Hello everyone, welcome to today's lecture. Today I will be doing the organic questions of the GATE 2018, the next 5 set. So the questions included in this lecture will be question number 6, question number 26, 27, 28 and 29. Right. So let's start with the question number 6. The question says the major product formed in the following reaction sequences. So you are having this molecule. So this molecule, as you can see, it has a lactam ring. Lactam ring is basically amide RCONH2 or RCONHR, but when it is cyclic it is called as lactam ring, and to that you are basically reacting kind of tosyl azide, because N3 is there, and only if this would have been CH3 it was tosyl azide. So it's kind of tosyl azide which is little acidic here, and then second step you are adding rhodium acetate. So this is a famous reaction. So if you look at the starting material, let me show it here itself. If you look at the starting material, these two protons are slightly acidic, right? These two protons are slightly acidic. So that's why this carbon it is called as, this CH2 is called as active methylene group, because you can remove these two protons not in one step but in two steps, because carbon cannot stabilize two negative charge at one step. So basically in two steps you can remove both the protons, and the negative charge which comes is gets stabilized over this carbonyl group and this ester group, and therefore this is called as active methylene group. So now active methylene groups, when it reacts with azide molecule, basically tosyl azide, they form diazo compound, which later in presence of rhodium acetate it gives you carbene. So these are the first two reactions which are known reactions, and after that you will have to look for this molecule what all things can happen. So let's start with the starting material. So starting material, this is the active methylene group, and you are reacting with tosyl azide, so it will give you diazo compound, and this diazo compound in presence of rhodium acetate, it will basically what happens is this bond comes up and you get negative charge on the oxygen, and then when it comes, this negative charge comes on the carbon. So basically 2 electrons comes here and this goes out, so it takes away the electron from the carbon. So the carbon remains neutral but it gets 2 electron, so it is called as carbene. So carbene is, its octet is not complete, it's electron deficient because only 6 electrons are there, but still it is neutral. So this is the basic reaction. Now we'll look at our reaction. Okay, we'll go down. Let's look here. So in this molecule we have this active methylene group. So first step, you are having this azide molecule, so first you will get your diazo compound. Okay, then once you get this diazo compound, next step you are adding rhodium acetate. So as we said before, this nitrogen is having positive charge, this nitrogen having negative charge, so this negative charge comes in here, this bond comes here and this gets delocalized, oxygen get negative, then this comes back again here, the carbon gets 2 electrons here, kind of negative charge, but this N2, N2 is a excellent, one of the best leaving group, because very stable, between nitrogen triple bond is there, so very stable. So this goes out and you get carbene. So hereafter we have to see what all things can happen. Now carbene, as we talked about, it is electron deficient in nature, so it is electrophilic in nature, it loves electron, right? So what is the nearest electronic rich center we have here is nitrogen with lone pair. So nitrogen, nitrogen's lobe is much larger than that of oxygen, because nitrogen is less electronegative, so it does not hold its lobe very close to itself, so lobe is bigger, so it attacks. But to understand, here nitrogen will not be very nucleophilic. Why? Because it is amide, so this nitrogen lone pair gets stabilized over this, therefore amides are not at all basic, but to a certain extent they are nucleophilic, and that's what is being exploited here, and the lone pair goes and attacks here and you get a bond, and now it was neutral, now it has gained 1 electron, because when nitrogen is sharing the electrons, when it is forming bond, so basically 2 electrons were with nitrogen, when bond is formed, 1 electron it keeps to itself, 1 electron gives to carbon, so carbon gets negative charge, the negative charge takes this proton, this goes back and you get this neutral this molecule. So the answer was A. So if you know the first two, that was In tosylazide, formation of diazo compound takes place, and then acetate that diazo leaves and forms carbene. You will be able to solve this question. Moving to the next question, that is question number 26. So you are having this molecule. So what is this molecule? Basically it's a aldehyde. On to the aldehyde alpha position we have a chiral carbon. So when chiral carbon is there, regioselectivity comes into picture. It's never regiospecific, it's always regioselective. So difference between regiospecific and regioselective is, first what you should understand, regio means region, which side will attack. Okay, so it gives different stereo product. I should not use the word regioselective, that was wrong, sorry. I should use the word stereoselective. So this, whenever you are having alpha carbon which is chiral, the reaction is stereoselective and not stereospecific. Stereospecific means you get only one stereoisomer, whereas when you are talking about stereoselectivity, it means one of the stereoisomer will be major and other one will be minor. So that is being reacted with this allylic compound which has silane on it, trimethyl silane, and you are reacting in presence of TiCl4. So TiCl4 you should know is a Lewis acid. Okay, so it accepts lone pair of electron basically, and you are getting X and Y. Question is, X is major product and Y is minor product. Quite possible. X is only product, definitely not possible, because just now we said it has to be selective, not stereospecific. Y is the only product, this also is not correct. And then it says X is minor product and Y is major product, this also is possible. So we have to see between A and D which is the right answer. Now this molecule is important to understand lot of concepts. Whenever you have allyl silanes, so allyl, you know, double bond, and then you are having CH2, that is called as allyl. So on the allylic carbon you are having SiCH3 thrice, so it is allylic silane. So these are very stabilized. Why they are stabilized is because this SiMe3 is parallel to the p orbitals of this pi bond. So what happens, this pi bond gets stabilized, starts sharing electron with this silicon, this carbon silicon bond. So you know silicon has vacant d orbital, so they stabilize. So this can give electron, basically silicon is when we go down, electronegativity reduces, right? So silicon is less electronegative than carbon, so it can give electron to this carbon and therefore it stabilizes positive charge on the carbon. So on the beta position if a carbocation is there, and on the beta position if you are having silyl group, so this is stabilized because silicon gives electron. See, silicon is less electronegative, so it will not pull electron, rather it will give electron. We can say in the right word, carbon is more electronegative than silicon. So carbon takes electron from silicon, and silicon has big orbitals, so it overlaps quite well at the beta position and gives electron. Therefore carbocation on beta position to silane is very, very stabilized, right? Let us see what happens here. So basically when you have silane group, allylic silane, and you react it with the electrophile. My cat is disturbing actually. One second. Yeah. So what happens is, when electrophile is there, electrophile will never get added from this carbon. It will get added from this side because you get positive charge on the beta position to silicon. So this is stabilized. This positive charge, this carbocation is stabilized by this silicon. Why? Because just now we saw this p orbital will overlap with this carbon silicon bond because they both are parallel, and this will give electron, and if it gives electron, positive charge will be reduced and therefore stabilization happens. Okay. Now what is the role of TiCl4? TiCl4, as I told you previously, it is a Lewis acid and it helps in activating the electrophiles, right? Let's solve this question now. So if you remember, whenever you do Friedel-Crafts alkylation, Friedel-Crafts acylation, you always add some kind of AlCl3 or something like that, you add always a Lewis acid to activate the electrophile, to make the electrophile more reactive. You basically want this carbon to get more positive polarity, so that it gets more positive polarity, so that nucleophile can attack on it, right? So that's what is the idea about adding TiCl4. So when you have TiCl4, this oxygen lone pair goes and attacks on this titanium, and this Cl minus leaves, and you are getting positive charge on oxygen. Oxygen was already electronegative. It was pulling the pi electron closer to itself. So the pi orbitals are closer to oxygen than the carbon, and therefore carbon had positive polarity. Now oxygen has become much more electronegative because of the extra positive charge. So lot of positive polarity on this carbon. So basically its electrophilicity has improved, right? So what happens? Next step, you can see here, this silane, silane, allyl silane was there. You know, alkenes in general, you should always know, alkenes always undergo electrophilic substitution reaction. So they go and attack, they act as a nucleophile, and they attack a electrophile. So as we said, the attack will happen from this side and not this side. Remember, this attack will not happen from this side, because that side will not give you beta carbocation. So the attack happens from this side, and you get a beta carbocation here. Now beta carbocation is stabilized. Why? Because this p orbital and this bond, they are next to each other and they overlap and they stabilize. So what happens next is Cl minus goes and attacks Si. Remember one more thing, silicon, like trimethylsilane kind of thing, no, they act as hard acid. Hard is like something like proton. So they have very, very concentrated positive polarity. So you cannot polarize it much. So it is always attacked by hard nucleophiles. Something like F minus. F minus is the best nucleophile which will attack on silicon, and always it attacks, very strong affinity for F minus. Then comes O minus, and O minus or O2 minus. Then also comes Cl minus, because Cl minus is also quite electronegative. So this Cl minus will attack, and this goes down here, and you get your double bond. And then double bond, and this OTACl3, no issues, you just hydrolyze and goes off, and you get OH here. Okay. Now what happens is, we have to look at the stereochemistry. So basically what has happened on this C double bond O, you are attacking that silane group, so that this double bond O becomes OH, and the allyl group gets added, and that silane will be removed by Rani nickel. Okay. So that's what is happening here also. Once again, I will just show you. What was happening is, this double bond aldehyde is there, this silane group leaves, so this comes out, you forget this TiCl3. So what happens is, this becomes OH, and this allyl group gets added with the silicon, and that silicon can be removed with this one. So basically you are adding allyl group on the on this carbon. So why they have asked such a simple question? Because this question is not that simple. They are looking at your understanding about stereochemistry. So because to the alpha of the carbonyl group, you are having this carbon which is chiral. Okay. So because this carbon is chiral, so this will determine how the nucleophile will approach, from which direction it will approach, and that is that you can find by what is called as Falkin-Hahn model. Okay, Falkin-Hahn model. So let's draw first Newman projection. So if you look at the molecule was this, right? One second. This was the molecule. So C double bond OH was there, and CH3 was front, and H is in the, and pH is in the plane. Let us see once again the starting material. Yeah, this is the starting material. So basically this CHO is in plane and this pH is in plane. So they both are parallel to each other. This CH3 is coming towards the viewer. Carbon valency is 4. So one hydrogen is also there. So that hydrogen is away from the viewer. Okay. So hydrogen away from the viewer. So basically what we are seeing is this C double bond O is in between this CH3 and hydrogen, and pH is in the plane, right? Yeah, so that's what it is. Now what we are doing is we are just catching this part, you understand, just catch this pH and bring it front. So this CHO goes inside the board, this CHO goes inside the board, pH is coming outside the board. Okay, so what you will see, oh, I have done other way around, so we can do other way around also, doesn't matter. I would explain other way around, so let's go with that. So you could have done that, but what I have done, let's go with that. So what here I have done is I am pulling the CHO front of the outside the board, and this one is going inside the board. So what is happening, this pH is going inside the board, it remains in front of CHO, and this hydrogen and this C and pH bond, they both are parallel. So you can see this pH, this CH and this pH, they both are parallel. Okay, and what else is there, C double bond O, you can see it is outside the board. So this C double bond is also outside the board. Now what you see, this C double bond O was in between CH3 and H. Now when you have pulled it this side, so what you are doing is basically this goes behind. So when it goes behind, this H comes to the right side and CH3 comes to the left side, and that's what I have done. Please don't move ahead. If you don't understand, pause it, think about it, and then only move ahead. Nothing much. I am just holding this hydrogen and pulling it in front of the board, so it is coming out of your screen, and this whole thing is going inside. So when whole thing is going inside, what is happening is H is going to the right side, CH3 is going to the left side. That's what is happening. Okay. Now to apply Falkin-Ahn model, what we have to do is, to this C double bond O and H, basically they are in a straight line. You see it's coming little, this H is not in the straight line, it's coming outside the board with little bent, but because we don't have 3-dimensional, so we are drawing it like this, and the bulky pH will be perpendicular to CHO. See this bulky pH has to be perpendicular to the CHO. So how can we do this? You see this pH is in front of this H. This pH is in front of this H. Now to get it, this so if I want to get this CH and this pH perpendicular, I have to rotate this 90 degrees. So I can pull it outside the screen, right, or I can push it inside the screen, either way. So I can rotate it 90 degrees clockwise or anti-clockwise. So here what you have done is, you look at this molecule. So this is what we have done. This is the previous operation where we converted sawhorse into Newman projection formula. So what we are doing is, we are rotating this pH 90 degrees. So this makes our job very simple. So this makes our job very simple. 1 second, that's my cat which disturbs every time, right? So when you rotate it like this 90 degrees, what happens, this pH comes here perpendicular to it, and then when you are rotating 90 degrees, CH3 comes this side. So CH3, which was this side, is still, it is top, but from the left side has come to right side, and this H has also gone 90 degrees, so it has come down. Is it clear? So that's what has happened. pH has come here and CH3 stop, H is there. Another thing which can be done is, rotate this pH 90 degrees to the right side. So what will happen, if you rotate like this, this CH3 comes down, this H goes up, and that's what you are getting, this H and CH3. Now both of them will take part in this reaction nucleophilic attack, and whichever attack is more favored, that will give you major product, and whichever attack is less favored will give you minor product. But we have to understand, first we have to look for the chiral carbon. So that chiral carbon was alpha to it, and we have to see the bulkiest group. So among CH3, H and pH, pH was bulkiest, and therefore you have to rotate so that pH, the bulkiest, comes 90 degrees and not anything else, either clockwise or anti-clockwise, right? And then after that you have to see how the nucleophile will approach. Now nucleophile can approach, it will approach, basically you know that tetrahedral angle is 109 degrees, but it attacks from what is called as 107 degrees, called as Bourget-Dunitz angle. they have found all this, they have calculated, and they also found experimental observations. So basically it's 107, so you can think as 109 degrees and think about it, attack will happen. So if this is the C double bond, 90 degrees is this, so 107 degrees becomes something like this, attack will happen from here. Now 107, attack can happen either from this side, or it can happen either from this side. Either side it is fine. Okay, so now from which side it will happen? If attack happens from this side, pH is there, pH is very bulky, so it will not happen from this side. Remember this is forbidden because pH is bulky, so it will not happen from this side. This side is very favorable. Why? Because hydrogen is very small. Hydrogen is smallest atom, it never ever gives any kind of steric hindrance, so therefore this will be very favored and it will give you major product. Okay, so let us see what should happen. So if nucleophile attacks from this side, this OH will come here, so you can put nucleophile this side here, you can put this OH on this side, and that will be your product. Okay, so it is pushing from this side, so it pushes little this side, and therefore OH comes here and nucleophile comes here, right? Another one will be when pH was 90 degrees towards the right side. Now when towards the right side, 107 degrees attack can happen from here, it can happen from here. Again we said attack cannot happen from this side because bulky pH is there, but attack can happen from this side because CS3 is not as bulky as pH, but definitely nowhere compared to hydrogen. Compared to hydrogen, CS3 is very bulky, so it will be very minor product, something like 5% or so. 95% will be attack, so that pH was on the right side, on the left side, and hydrogen was on this side. Okay, so that would be major product and this will be minor product, so this will go on attack. Minor will be really minor, some 5% product. Okay, and therefore you will get two products that are so let's see which is the major, which is minor. So major product, let's see. So when pH was this side, we said attack happens from this side because hydrogen is very small, so this allyl position is going attacking here, so it is pushing this side here, so allyl will come here, allyl you make it 90 degrees, and this OH comes here. Basically you have to maintain the 107 degrees, so you are pushing both 109 degrees, sorry, because it's tetrahedral, so you are pushing this hydrogen, this OH this side, and you are getting this product, right? And when you attack from this side, this is also, this gives you the minor product, so this is the minor product. So let's find out what is out of major, which is X and which is Y. So yeah, so this was your X, which was the major product from where hydrogen has attacked. Now what we are doing is we are rotating this 90 degrees up and this one 90 degrees down, so that I am putting this bulky group and this bulky group anti to each other, right? So they are already 90 degrees, I am just rotating the whole molecule, because you can see, sorry, 180 degrees to each other. You can see that this allylic group and this pH, they are 180 degrees to each other already. Here also they are allylic. So if you don't understand, you can do two things, like you rotate 90 degrees here and rotate 90 degrees, sorry, and then you can rotate this pH this side 90 degrees. Otherwise just whole molecule you are pushing it up, so you are getting this. And then what you are doing is two operations. The next operation what you are doing is you are rotating it 180 degrees. So you are rotating it like this. So basically you are turning this whole molecule 180 degrees. Okay, so when you rotate this whole molecule 180 degrees, so this pH and H and CS3 which was behind is coming front, and this allylic position, this OH and H which is front, goes behind. And then what you are doing is you start looking from this side, so you just turn it little like 90 degrees, again you twist. Okay, you turn it that side 90 degrees. So when you are turning 90 degrees, what happens? This H is going behind the board, correct? This CS3 is coming front of the board, and this pH remains in the plane. So that's what you are doing. This pH in the plane, CS3 is coming outside the board, this H is going inside the board. Please don't move ahead if you don't understand. It's very simple. I am just lifting this molecule, rotating 90 degrees inside, so that what happens is this CH3 is coming out and this H is going inside, right? Think about it, it's not hard. So when you are rotating like that 90 degrees, what is happening? This H is coming front, this OH is coming front, and this H is going inside, and this allyl remains in the plane. So that's what is happening. This allyl remains in the plane, this OH is coming front and H is going behind. Okay, so this is your X. See, I would have done all this calculation because I would have seen the products, and I was trying to make as X from here. Similarly, so X is the major product and Y is the minor product. So A is the right answer. Next question: the enantiomeric pair among the following is. So you have to find out which among them are enantiomeric pairs. So what is the definition of enantiomers? Enantiomer definition is two stereoisomers which are non-superimposable on each other but are mirror images to each other. So basically on the chiral center, both the substituents, two of the substituents flip their position, then it is possible. If more than one chiral centers are there, then in all the chiral centers two substituents have to keep flipping the position till all the chiral centers have flipped the position, then you get the enantiomer. So basically for a molecule to be chiral, to show this enantiomer, pair of enantiomers, it should be asymmetric, it should be chiral, it should not have a plane of symmetry running through it. If you look at these two, this molecule clearly has a plane of symmetry, and therefore these two has to be identical. Let us go step by step. See this molecule. So this is coming out, this carbon bond, this carbon bond is coming out and this coming inside. So imagine this paper itself is cutting into two halves. So what is happening? This part is going inside and this part is coming outside. So these are cut exactly into two halves, and this CH3 is a ball, so it is cutting two halves, this hydrogen into two halves, this CH3 into two halves, and this H also two halves. So it is being cut exactly into two identical halves. That means there is a plane of symmetry, it is achiral. So there is no way it can have enantiomers. And you can also look that they both are identical. So this was what was given A and this is what is given B. They look like mirror image. Correct na? Because when you look at the mirror, what do you see first? You see nose, because nose is coming out. Similarly here CH3 is coming out, so through the mirror you will see this CH3 and everything is fine, looks like mirror image. But if it is superimposable, that means they are identical, they are same. So it is not mirror image, actually they are identical. So what I have done is I am rotating it 180 degrees. How I am rotating? I am just rotating it like that. Okay, I am just flipping it that side, so that this CH3 comes out this CH3 comes out this side and this CH3 comes out this side. Now you can see, now you just lift this molecule and put on this. So this CH3 sits on this CH3, this CH3 sits on this CH3, everything else sits on each other. So therefore they are identical, they are superimposable. If you look at this option B, so this is alene. Okay, alene does not have plane of symmetry if both the substituents on either side are different. So they will have enantiomers, but are these enantiomers? That we don't know. Alenes, what happens is these two carbons, they are linear, okay, because it is sp hybridized carbon, the center carbon, this carbon is sp hybridized. So two of the substituents, these two substituents which I have drawn in the plane, they are on the board, okay. This Cl and this H are on your screen, whereas this H is coming outside the screen and this Cl is going inside the screen. So how much ever you try, you will see that there is no plane of symmetry. Imagine you are having some, you are making some this kind of symmetry. So what happens? You are not seeing both sides, because if you move from here you get Cl, but if you move from here to here you get air, right? Because this hydrogen is coming out, you are not getting anything else. Similarly, if you cut plane, this think this paper as this board as the plane which is cutting, then what happens? If you come outside the board, outside the screen, you are finding hydrogen, whereas if you come outside the board you are finding air. So therefore they are also it is not plane of symmetry is not running, so it will have pair of enantiomers, but is this A and B enantiomer or not, we have to find out, okay. So I had done this calculation in mind, and I will tell you what I basically did. So this B is there, no, you just rotate 180 degrees. So I am just rotating it 180 degrees. So what happens, this hydrogen is coming here, it was top, it remains on top, it was in the plane, it remains in the plane, Cl was down, it remains down, but in the plane, only difference is from right side I have rotated like this, so that becomes 180 degrees. So from right it has become left, and when this one rotate 180 degrees, what happens, this Cl which was front is going away, this hydrogen which was behind is coming front. Now if you see A and B, now this is B and this is A. See this, Cl is away from the viewer, H is towards the viewer. Here also Cl is away from the viewer, H is towards the viewer. H is top, Cl is down. H is top, Cl is down. So they both are superimposable, so they are identical. Looking at this molecule, so this molecule has a plane of symmetry, actually speaking. Is it? Let me look at it. No, they don't have plane of symmetry actually. No, they don't have plane of symmetry. If I cut it like this, I cannot see it because it goes down. So this is again kind of atropisomerism. You need not bother, we'll see about it later. But basically, it does not have plane of symmetry. So it should have pair of enantiomers, but are these enantiomers? We don't know. So what I have done is this side, this is there in the plane, this is towards the viewer, and this is away from the viewer, right? It looks like mirror image to me. Why it looks like mirror image? Because this is coming outside, here also it is outside, C double bond O, C double bond O, this is away from the viewer, but this part is coming outside the board, this one is inside the board, so it is not mirror image. Sorry, not outside, this is in the plane, sorry. So this is below the plane and this is control, so this one is below the plane and this is above the plane. When you look at your mirror, you cannot see that lip is on your forehead. So similarly, if this is down, it should have been down if it was in the, it was mirror image. So are they superimposable? Are they same? That we have to find out. So first thing what is being done is, on the B, two operations are being done. First rotate it 180 degrees upside down. So I am rotating it like this. So what happens is CO which was top CO has come down. But when you are rotating like this, which was front, this C double bond O which was front has gone behind, because whole molecule is rotated, and so this has gone behind and this normal CC bond has come front. Okay, and then you are rotating again 180 degrees like this. So when you are rotating it like this, what is happening is this bond comes here, this whole thing remains planar, and this comes this side. So this which is away from the viewer has come towards the viewer, and which is towards CC bond that has gone away from it. Okay, it's not easy, you will not understand immediately. Use pen and paper, think about it, practice, and then only move ahead. And then after that you will see that A and B are exactly identical, so they are also not pair of enantiomers. So very clearly D will be the answer. So this is again case of atropisomerism. Atropisomerism is basically this, if this rotation was free, then no question of stereoisomerism comes. But because these are bulky substances, they don't allow them to rotate freely, and because of restriction of rotation, this isomerism comes into picture, that is called as atropisomerism, right? Now let us look at this and this. Understand, this bond is outside the board, so this NO2 is coming outside your screen, and this COH is coming inside your screen, right? Whereas this NO2 is in plane, this COH is in plane, and then you are having this molecule. Now are they looking mirror image or not? That's what we have to look. So if I look into it, what happens is this carbon is there, this carbon is there, and here NO2 is coming front, but here COH is coming front. So that is the problem, that we are not sure, but these two are same or not, that also we have to find out, are they superimposable or not. So first operation what I did is rotated 180 degrees. You can say how you suddenly rotate 180 degrees, because thinking goes in. I always try to look that are they superimposable on each other. So I will try to make it exactly like B. I will try to make it like A by various rotations, and if that's not possible, then I will see if they are mirror images by some operations. So all that goes in the head, you have to practice. Okay, so I am rotating this 180 degrees like that. So when it goes like this 180 degrees, then what happens, this comes out. So this COH goes behind the viewer and H comes front the viewer, correct? So COH goes inside the board, NO2 comes towards, and when you have rotated like this, this NO2 was up, remains up. Only thing is from right it has gone to left position. This COH which is below remains below, only from right it has gone left. Then again I am rotating 180 degrees. So when I am rotating 180 degrees, what is happening? This COH goes top, NO2 comes down, and then what happens, this NO2 which was front of the screen goes inside the screen and COH comes outside. Now you can see that A and B are not superimposable on each other and they are mirror images. So this was basically A and this was basically B. So you can look here now after all that rotations, right? This is what we have got B. So you can see that this NO2 is front. So here NO2 is front. COH is inside this board. This COH is inside the board. This is above. This is above, and this is below. This is below. So they're exactly mirror image to each other, and they are not superimposable. I have tried all that and I have seen they were never superimposable on each other, and therefore D is the answer, right? Please practice, it's not very easy. Next question is very simple. It's not very simple actually, they made it quite complicated. It looked very simple initially. So you are having sulfur with sulfonium with positive charge. So very clearly, if sulfur is having positive charge on the neighboring carbon, very easily negative charge will come, right? And they form what is called a sulfur elide. Why sulfur elides are stable? Sulfur elides, phosphorus elides, both are very stable, because if negative charge comes on the neighboring carbon, the negative charge is delocalized, the electrons gets delocalized on the d orbitals, vacant d orbitals of sulfur, and therefore they are quite stable. You get kind of double bond between sulfur and the alpha carbon. So first thing what you are adding is potassium tertiary butoxide. Potassium tertiary butoxide is a very powerful base, but horrible nucleophile, will never act as nucleophile. Why? Because see, K plus is there, and you are, oh my god, what's happening, and you are having O minus, and you are having tertiary butyl group. Okay, so this is, so this is a very bulky tertiary butyl group, so bulky that it will never approach a carbon. It will only abstract the small hydrogen. So that is a very powerful base, but very horrible nucleophile. Second thing what we are adding is Rani nickel. So Rani nickel, no, very strong affinity for sulfur. So though they just write Rani nickel, it is always in presence of hydrogen. You put hydrogen in the balloon and you put Rani nickel. So that is for reduction. It will just remove sulfur and put hydrogen. So whenever sulfur elide is there, no, we talk about stabilized sulfur elide or unstabilized sulfur elide. So stabilized, let us see, I'll be talking about it. So first thing, when it attacks the base attacks, it removes the proton. So now proton can be removed from this CH3 or this carbon. So here if it removes proton, because this is also alpha, what you are getting is basically, if you remove proton from here, you will get secondary alkene, right? Sorry, you will get a secondary carbanion, but primary carbanion is more stable than secondary. But the problem is, secondary carbanion are not as stable as primary carbanion. Both are unstable. Basically anything which is charged is not stable. But when it is secondary, you are having more pumping groups. Hydrogen does not pump electron, but alkyl group pumps electron and therefore increases negative charge on the carbon which is having negative charge, and therefore this proton will be removed from the either of the CH3. It is same, not this proton, right? And you are getting this sulfur elide. Now this is unstable sulfur elide. Why it is unstable sulfur elide? Because if sulfur had double bond O, then this negative charge would have been resonance stabilized by this S double bond O, okay? But here all that does not happen. So generally when you are having negative charge on unstabilized sulfur elide, then what happens? It undergoes, when you are having alpha beta unsaturated ketone, if you are having alpha beta unsaturated ketone, it will go and attack C double bond O because it is not stable. So it will not look for thermodynamic stability of the product. It will go and see wherever there is more positive charge, it will go and attack because the negative charge is not stabilized. So you know, on this carbon lot of negative charge is there compared to this. Here also certain amount of positive charge is there. I am talking positive charge. If I told negative, I am sorry. Here also positive charge is there. Here also positive charge is there. Why positive charge is there? Because you know, this resonance is possible. This comes up here and this comes here, and you get kind of positive polarity here. But on this carbon, there is tremendous amount of positive charge on the carbonyl. So generally, if negative charge is there which is not stabilized, we will always attack at position 1, 2 and not at position 1, 4. But if the sulfur had been having double bond O, this would have been very stable, and so because it is stable, it will not go for attack. It would not go for attack. Wait, let me draw this as double bond O. It will not go for attack here, rather it will go attack here because you are getting cyclopropyl ring. Carbon-carbon bond, see, C double bond O is much stronger. To breaking it is not thermodynamically good thing to do. Whereas carbon-carbon double bond is weaker. So if you break this and you are forming carbon-carbon single bond, that gives much more stable product. But if you are breaking this C double bond O and leaving C double bond C, that is not giving stable product, because C double bond C is not as stable as C double bond O. You are breaking a stable bond and leaving the unstable bond together. But here the problem is, so that's why this was a tough question. Here the problem is, if by what I said logically, it should have attacked here on this carbon, okay? But when it attacks here, what happens? You can see it is going through a 7-member transition state. 1, 2, 3, 4, 5, 6 and 7. 7-membered ring is not neither kinetically nor thermodynamically favorable. So 7-membered ring will not form. Remember this always. 5-membered ring is kinetically favorable, thermodynamically also favorable, and 5-membered ring is kinetically more favorable than 6-membered ring, whereas 6-membered ring is thermodynamically more favorable than 5-membered ring, and therefore this rather than attacking here, it rather attacks here, because now it is 5-membered ring, because it is 1, 2, 3, 4. Sorry, did I do some mistake? 4 is here and 5 is here. So it goes through 5-member transition state. Because I got very surprised. 4-membered ring is neither kinetically nor thermodynamically favored, worse than 7-membered ring. So it will attack on this carbon, and this is what happens always in when sulfur elide attacks. You get either cyclopropyl ring or oxirane ring. You always get a 3-membered ring. Remember this, you don't forget it. And therefore this goes and attacks here, you get a negative charge, and this negative charge goes and attacks here, and this sulfur goes out, and you're getting a 3-membered ring. Okay, and you're getting a 3-membered ring. Otherwise, if you would have attacked here, then what you would have got is 3-membered ring, but with a oxygen in between. So it was oxirane ring, epoxide kind of system. But when it attacks at position 1, 4, so basically you are adding this CH2 between this carbon and this carbon and this carbon. Look at it. Okay, between this carbon and this carbon, this CH2 is getting added. Right? Think about it. It's very simple. Let me make you think once again. This CH2 goes and attacks on this carbon. This bond comes here. You get negative charge. negative charge goes and attacks again the same CH2, again the same CH2 and this sulfur elide. This sulfur takes back electron, and this CH2 is which is getting added. This CH2 is what is getting added, and therefore you're getting a cyclopropyl ring, and this sulfur goes out. And then use Rani nickel. Rani nickel reduces, just removes this sulfur, and you are getting this CH3. So the product is A, right? Moving to the last question. Moving to the last question. Now this was quite complicated question. So you are having this molecule where you are having ketonic group and you are having alkene, and you are reacting first with MCPBA in presence of base, then you are reacting with sodium hydroxide water, and then last you are reacting with iodine, potassium iodide and sodium bicarbonate, right? So MCPBA, what does MCPBA does? MCPBA, you know, it is superacid, metachloroperbenzoic acid. So not superacid, called as peracid or peroxy acid. So it gives one oxygen, active oxygen. So it should give two reactions. One reaction is it can form epoxide here, that's what it does, it forms an oxygen ring here, or it will undergo Baeyer-Villiger oxidation. So Baeyer-Villiger oxidation is between C double bond O and the carbon, oxygen gets inserted, so you get ketone. But thing is, that's why it was complicated question. This alkene is masked by this CH2OMe group, so it covers it up. It does not allow MCPBA to reach here, okay, and therefore this double bond remains untouched, and the reaction happens on the ketone to give Baeyer-Villiger oxidation. Please remember this, okay. Now Baeyer-Villiger oxidation, I'm writing the mechanism, I'll explain you, but basically oxygen gets inserted. So you can think oxygen can get either inserted here, oxygen get either inserted here, okay. So oxygen will not get inserted here, oxygen gets rather inserted here, because if you look at the mechanism, no, it goes to something like carbocationic transition state, electron deficient transition state. So if this moves, this is CH2, this is CH2, so this will have primary carbocationic character. Whereas if this moves, no, it is having this carbon is having one hydrogen and two alkyl groups, so it is having secondary carbocationic character. So secondary carbocation is more stable than primary carbocation, so oxygen always gets in between the more substituted carbon. So oxygen will not enter between this carbon and this carbon, rather it will enter between this carbon and this carbon, and that is what is called as Baeyer-Villiger oxidation. So let's look at the mechanism. So ketone is there, so ketone lone pair goes and attacks this proton, and this gets negative charge, and this negative charge goes and attacks here, you get this one, and then this bond moves in, and this goes and attacks here, and this goes and basically picks up this proton, this comes out as acid, and that's how you are getting ring in between. So it goes through this transition state. See this transition state is having positive charge, so this positive charge is spread around between these three. So now this carbocation was stable or this carbocation is stable? Of course this carbocation is stable, because it is secondary carbocation. Had it happened from this here, you would have got this side, would have got primary carbocationic character, and therefore oxygen gets inserted in the more bulky position, and you are getting this ketone. So this mechanism, no, it is easy but quite confusing many a times. So please look into it once again. Oxygen attacks this proton, then this negative charge goes and attacks, this comes up, you are getting this, and then this moves in, and this goes out, and this leaves again, okay. So it's not that tough actually, right? So once this is formed, and then you are adding sodium hydroxide and water, so basically you are hydrolyzing ester. So when you hydrolyze ester, this will cleave up, and you are getting OH and this COO. Now see why I said this is complicated question, because stereochemistry was involved. Now look at this carbon, okay. This carbon, you can see very clearly, you can see very clearly from the carbon 2, this carbon 2 to up 1 is going above the plane, whereas this is CH2COO minus is below the plane, correct. Similarly, if you look here, this bond is going above the plane. If you think this as planar, and this OH is coming down. So that means this OH and this CH2CO minus, they are in one plane, and because they are going below the plane, they will be away from the viewer, and this part will be above the viewer because it is going up. So that's what we have drawn. This COMe, this is going above the plane, so it is towards the viewer, and this OH and this CH2CO, which is going below the plane, that we have put as away from the viewer. Next step is very simple. This is iodoelectronation. This is a very famous named reaction. So you put iodine. Next step you put iodine. So of course iodination will happen at the double bond. Now it is no longer masked because from 6 member it has become 5 member ring. So this goes and attacks C to get a positive charge, and then CO minus will attack. So it will attack kinetically because negative charge is there. So 1, 2, 3, 4 and 5. So it will go and attack here, and this comes out here, and you get minus charge. So the answer is A. So this was simple electronation reaction. You can ask why it does not attack on this carbon. It can attack this carbon, but it is bit tough, it is far. So kinetic takes over thermodynamic. 6 member ring, and 6 member ring would not have been very stable because it becomes very, very strained. Rather it forms here 5 member ring like that. Okay. And one more thing is, see, this iodination, when it is happening, this iodine is attacking from front. Why it is attacking from front? Because see, next to this double bond, this OH is away from the viewer. So this is bulky. This also is bulky. So the iodine to come from behind is very, very tough because these two bulky are there. So they attack from front, and therefore I plus is getting attacked from the front. Now because bonding orbital is towards the viewer, that means anti-bonding is away from the viewer. So this will attack always behind, and this comes out, and therefore this forms bond behind, and this iodine is plus. Please remember, attack always happens on anti-bonding orbital because that is vacant, and anti-bonding orbital is always 180 degrees to the bonding molecule orbital. So if bonding molecule orbital is front, as it is here, and therefore anti-bonding will be behind, so attack happens from behind, and you are getting this product, which is A. That's it for today. Thank you very much.